Good morning once again. I welcome you all for the second lecture on digital logic circuits. So in the previous class, we saw what is digital logic, right? And what is the need for digital logic circuits and the advantage of digital systems over analog systems, right? And we'll just continue what we just left in the previous lecture. And here we'll start with what is a circuit, right? What is a circuit and what is the purpose of having a circuit? So behind every task there will be an automation, right? So if you want to transmit power, if you want to transmit data, or if you want to transport something from one place to the other, we need a connectivity, we need a network, right? So for example, if you are manufacturing sugarcane and if you want to transport that sugarcane to a sugar mill, right? We need a type of transportation and we need networks and we need communications between the farmer and the sugar mill, right? So we need a connectivity, not just physical connectivity, we need a communication also, right? So that gives you a circuit, right? Circuit is nothing but, it is actually a network. So for example, if you are watching a Formula 1 race, right, they call it a circuit, right? The race track, they call it circuit, and each circuit will be having a pit stop, and you know that, right? And the people will be racing around. It may be a bike race or MotoGP or Formula 1 race, right? So whatever. So it is actually a network, and every circuit will be having a source and a destination, right? It may be voltage source or current source, right? There will be a source that gives power to the entire circuit. Also, there will be a component that will absorb absorb maximum possible energy from the source. It may be current source or voltage source, right? This is a typical analog circuit, right? And we are going to deal with digital circuits. So analog circuits are required and also digital circuits are required. It depends on what type of application we are using, right? So I hope you understood what is a circuit and we can move further. And what is a circuit? And we're talking about DLC, right? Digital logic circuits. So DLC, digital circuits are present wherever. It is present in this projector, it is present in the remote here, placed over here, and it is also present inside this slide changer. So they are present in computers, smartphones. Actually your smartphone is actually a computer, right? So analog circuits differ from digital circuits in what way? Both circuits have sources, both circuits have loads and destinations, right? And in what way they differ? See, analog circuits, they supply power to the components, right? Inside what happens? They supply power to the components, they consume power and they do some work, right? And digital circuits, they perform some logical operations inside the smartphones and computers, right? So in the lower classes you might have studied about computers. Computer is a arithmetic and logic unit and it has a CPU, right? So arithmetic stands for addition, multiplication, right? Division and subtraction, right? And here what is actually logic? That is what we are going to study, right? The circuits that can do arithmetic and logic functions are called digital circuits, right? So digital circuits, they have their own advantage, own applications, right? Digital circuits have evolved vastly in the last 20 years, especially after the people started learning lots of programming languages. People started moving towards the electronics market. So things have changed in the last 20 years very, very rapidly, right? So what is electronics? We study digital logic circuits and sometimes we call it digital electronics. So what is electronics? Well, in electronics, semiconductors are involved, right? What about electrical? Machines are involved. Well, electrical machines are involved. Here we are talking about semiconductors, right? And electronics, they operate at low voltage. power electronics operate at high voltage, but digital electronics we operate at very quite low voltage levels. That we will see in coming classes, at what voltage level we will be operating the systems, the gates, and what kind of semiconductors we will be using, right? And what are power, we're not going to talk about power electronics, but if you are coming to electronic side, you need to know what is power electronics and why digital electronics is different from power electronics. Always do a comparative study so that you won't forget. Also, you will be getting lots of insights, right? So that will be seeing. So the basic difference is about major components of electronic circuits will be diodes, rectifiers, CMOS, and that will be seeing one by one. And there will be components that will be working at low voltage levels. So we saw that in the previous class, right? So this is the primitive computer which is having just 40 megabytes of storage, and this is actually a modern computer having more than 2 terabytes of storage. Very compact, you can take it anywhere, anytime, right? But this is not portable. It consumes lots of space and lots of power, requires lots of ventilation, and requires lots of skilled people to operate it. One small mistake, a small mistake in the wiring or small mistake in the in the circuit, entire thing will be going for a toss, right? So digital systems. See, this was the the best part of entertainment for the people from the 80s and the 90s, and this is for our generation. We people are doing, both the 80s and 90s and the 2K, we people are not for using this audio cassettes or VHS cassettes. We are going with micro cards, right? Micro SD cards, right? The storage space can be expanded up to 128 GB, sometimes 512 GB, right? Memory cards are available now. You can take the entire thing in your palm, right? You can take it anywhere and use it anywhere. You can store up to 10,000 or 15,000 songs, right? You can store large millions of data, documents, images, videos, right? But here the storage capacity of these two guys is very, very limited, right? This is limited up to 64 GB, but still you can store lots of data, right? Very, very easy to carry and access. So this is the advantage of digital technology. And just like we saw in the previous class, it is also all about communication, right? With the advent of digital systems, the communication industry has grown, has seen lots of peaks, right? So previously we were using this modulator and demodulator devices, analog devices. Now we are using digital devices for better quality communication anywhere, anytime around the world. Because of this digital technology used in communication, the earth has shrunken in size, and we call it the global village, right? So my favorite part is photography. And this was the camera my father was using, and this is the camera I am using, right? The difference being these two is you can click very nice photos, but the process of development of the photographs is different. Here you see it takes lots of time, around 15 to 20 days time to see a photo album, right? Consisting of around 50 photographs, maybe more than that, more days maybe. It requires on the skills of the developer. But if you are clicking photos in digital mode, you can make a Photoshop of it, right? And you can make corrections on the lighting and color, and you can go to printing directly, and you can have this album in 1 or 2 days, right? So time consumption, energy, effort, everything has been downsized by this digital technology, right? So need for digital technology, need for communication, automation, and storage of information. Storage and access of information, to be precise, right? So let's skip this, we'll see the last one. So this is the contents of our syllabus. First one will be digital families and digital communication, right? Combination logic circuit design, synchronous sequential circuits, study about this sequential circuits and its design, and asynchronous sequential circuits and its design, and last one, logic families and memory, right? These are the 5 units we are going to discuss in the further classes. And coming to number systems, and in our syllabus we are given with 4 number systems: binary number systems, octal number system, decimal and hexadecimal number systems. So in binary number systems, we start with the nature of binary number system. How to identify? They have the base 2, right? So bi stands for 2, and naturally the base is 2, right? And octal number systems, octagon, right? So it means there are 8 components. So the base is 8. And decimal number systems, they have the base 10, and hexadecimal base number systems, they have base 16, right? So we will see one by one. So what is the nature of the number systems and how to identify them, right? And how to convert from one number system to the other. So before that, I just want to tell you what is the concept of least significant bit and most significant bit, MSB and LSB, right? For example, you have this digit here, 1247369, right? Very long digit, right? So how to identify the least significant bit and the most significant bit? The least significant bit will be on the rightmost corner, 9, right? 9 here is the least significant bit. Why? Because 9 has the least weightage given in this digit, right? So the digit which has the least weightage will be called as the least significant bit, right? And the digit which is in the left corner, leftmost corner, right? The digit called 1, right? It is called the most significant bit because it is carrying the highest weightage, right? So we can call it 1,24,700, right? So this one here, put it on the green color. This is carrying the most weightage, and 9 is carrying the least weightage. So we are assuming 9 has the LSB and 1 has the MSB, right? So the same thing can be applied for any number system given, even for binary numbers, even for decimal numbers, right? This is actually a decimal number system, octal numbers and hexadecimal number system, right? So in the lower classes in schools we might have studied ones, tens, hundreds, thousands, 10,000s, lakh, 10 lakh, right? So which one is in the ones position? 9 is in the ones position. And which is in the 10 lakh position? 1. So naturally 9 is in the ones position, 1, right? So least weightage is given. So we call it MSB. The 10 lakh position, right? 12 lakh 47,369, right? So 12 lakhs. So 1 which is in the 10th lakh position, we call it MSB, right? So MSB and LSB looks so simple, but their impact in converting from one number system to the other is very, very huge. So we can start with decimal number system. See, decimal number systems, we used to use decimal number systems in everyday life. So in schools we might have studied decimal number systems. We start with 1, 2, 3, 4, right, in schools. Add 0 to it, right? Add 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The 10 digits, right? These are the base of decimal number systems. So that is why 10 is the base of decimal number system, right? It starts with 0 and ends with 9. So all the other decimal numbers are the combination of these 10 digits, right? If take 999, they are all 9, right? 786, 786, it's all combination of 7, 8 and 6, right? So all the other decimal numbers are the combination of digits from 0 to 9. So there are 10 digits which contribute to the entire number system. That is why it is the base 10, right? For example, you have this number 7,392, right? This is actually a very, very flat number, flat digit, or whatever you call it. But if you put base 10, right, base 10, it becomes a decimal number. You are telling the world that this is a decimal number, right? How to expand this? See, this is in the ones place. This is tens place, hundreds and thousands, right? So how to expand this? If you expand this, it becomes like this. So 2 multiplied by 10 to the power 0. Anything power 0 is 1, right? So 2 multiplied by 10 to the power 0 is 1, right? And 9 is in the 1's place and 9 is in the 10th place. So 9 multiplied by 10 raised to the power 1, right? And then it come to 3, and 3 is in the hundreds place. So 3 multiplied by 10 to the power 2, and 7 is in the thousands place. So 3 multiplied by 10 raised to the power 3. Alright, so this is how you expand it. If you add everything, you will be getting 7392 base 10, right? If you are not mentioning the base, and you will be losing your marks. Also, this digit will be losing its significance. So if it is a hexadecimal number or octal number or decimal number, how will you identify? You can identify from its base. So next one is binary number system. And binary number system, it consists of only zeros and ones, right? We cannot see any other number apart from 0 and 1. So whatever the number you represent in binary number system will be a combination of zeros and ones, right? So since there are only 2 digits involved, we call it bi. So the base is also 2. 2 is the base of binary number system. Some textbooks, they will be given as radix. Base or radix represent the same, right? Please don't get confused. So this is a digit, and this is a digit, and this is also a digit, right? And this is the format in which your computers or smartphones will be reading the memory. You can give instructions using your keyboard, mouse or touch screen, right? That will be physical, and you can give inputs in English, but the conversion inside the CPU is taking place, so that the computer will understand only binary numbers. Some computers like Raspberry Pi, they can understand hexadecimal. Some computers like microcontrollers like Arduino, they can understand hexadecimal, right? So, and this is the language that is better understood by computers. They don't understand English. So octal numbers. Octal numbers, they consist of numbers from 0 to 7. So there are 8 digits, right? Since there are 8 digits, the base is actually 8. So 8 is the base of octal number system, right? So you can represent an octal number system like this: 73 base 8, right? 63 base 8, 77 base 8, 52 base 8. So if you are mentioning this base here, 8 as 8, and that becomes, naturally that becomes what? That becomes an octal number, right? If you are mentioning the base 10, it becomes a decimal number, right? If you have a string of binary numbers, zeros and ones, 1 0 1 1 1, right? And if you are mentioning the base 2, it becomes binary number, right? So last one is hexadecimal number systems. So hexadecimal number systems, also called hex, right? It consists of numbers from 0 to 9, right? 9, and from there is no 10 and 11, and after that we have A to F. So from alphabet A, B, C, D, E, F, and it starts with F, right? So if you count the number of digits, the number of digits will be 16. So if the number of digits are 16, the base is actually 16, right? The base will be 16. So whatever the digits we represent in hexadecimal will be a combination from 0 to 9, right? And from A to F. So there are 16 digits here, and the base is 16. This is very basic, right? So you can represent a digit like this: 0, F, A, base 16. If there is no base 16, the user will be confused. What is the number system used, and why is this number here, right? So please understand, you have to put the base here, so that it will be coming under the hexadecimal number system. Okay, this is how we have to represent numbers. So we have a number system conversion table that we will show in the next class. So how to convert from one number system to the other, it will be very useful for all of you. We have a table actually. We'll show it in the next class, right? And how to convert from one binary number to a decimal number. See, you have to convert this, and this is actually a problem, a 2 marks problem, or whatever you call it. So you have to convert 1101 base to into a decimal number. You have to convert this into decimal, right? What you have to do? See, 2, base 2 is a smaller base, right? What is decimal? Base 10. You are going from a smaller base to a bigger base. That means you have to multiply and expand, right? Multiply is nothing but expanding, right? You are getting bigger. So you have to do the multiplication within your digits and add them, right? See, we can start with here. So what is the first digit you have? You have 1, right? 1 is the least significant bit, LSB. It has the least weightage, so it is in the ones place, right? So 1 multiplied by 2 power 0. Why you are putting 2 here? Because you are converting from base 2 to base 10, binary to decimal. So you have to multiply these 2, right? You have to use this 2 and you have to multiply subsequently and add them, right? So that is why we have these 2 here. So the 1 is here. You can bring this 1 here, right? 1 multiplied by 2 plus next digit is 0. 0 is in the 10th place, right? 1's 10th, so 0. And 0 multiplied by 2 power 1, right? Plus we have 1 here, 1 multiplied by 2 power 2 plus last we have this most significant bit 1 multiplied by 2 power 3. Okay, so this one here is the least significant bit. So you are multiplying the base 2 with the least power. You are given with the least power. And this one is the most significant bit. So you are multiplying that with the most power, highest power, right? So highest power is from 0, 1, 2 and 3. 10 power 3 is the most highest power and you are giving it to the most significant bit, right? And if you are adding this, 1 multiplied by 2 power 0 is 1, right? And 0 multiplied by anything is 0 and 2 square is 4 and 10 power 3 is 1000. So if you are adding all this, you will be getting this result, right? So 2 power 3. I think, yeah, it is not 10 power 3, it is 2 power 3. There is a typography, right? That is not 10 power 3, that is actually 2 power 3. So 2 power 3 is 2 multiplied by 2 cross 2 is 8, right? So you get 13, right? This 13 is not just 13, you are converting this binary into decimal, right? So in the end, in the result, you have to write 13 base 10, right? So you have to mention the base so that you can finalize the result, so that you will get your full marks also, right? This is how you can convert from binary to decimal, right? Please understand, if you are going from a smaller base 2 to a bigger base 10, you have to multiply, right? How can you multiply? You can start with this least significant bit and you can multiply with the base 2, right? Least significant bits will be having least power, right? And the next bit and the next bit and the next bit. Keep on increasing the power, right? If there are more digits and you can add more components, right? You can multiply and add more components and the result will be different here, right? So in next class we'll be studying about logic gates. There are fundamental gates and derived gates, right? And universal gates also. We'll see one by one and the description will be given in the next class, right? So these are the gates we are going to study in the next class. AND gate, OR gate, NOR gate, NAND gate, right? XOR gate and XNOR gate, right? We will study the operation of each and every gates along with the truth table, right? So thank you all so much for watching, and if you have any doubts and if you have any problems to be clarified, you can put it in the comment section, right? We will be responding to you whenever we can, right? And that will be very useful for the other people also. So please make sure your comments are useful and respectful, right? So thanks for watching and meet in the next class.